So next week we have Charles' Law. And so what I'd like you to do before the lab, just skim through it or read through it. You don't have to read through it in heavy detail, but just have some kind of mental picture of what's going on in lab. And so today we're doing measurement. Have some kind of mental picture of what we're doing in lab. Because as you go on in science, and take higher level science classes, basically they're going to expect you to know what's going on, and what they'll have is like when I was taking most of my upper division lab classes, they started the class with a quiz, and so even before class you were supposed to know what was going on, and we'd have a quiz, and the quizzes weren't easy quizzes. You really had to know what you were doing in the lab and the concepts, theory, whatever else was being covered. Here we're just going to get a start. At least you should skim it. You skim it and then you look, does it make sense? If things don't make sense, make sure to ask at the beginning of class to get things clarified. All right, so experiment 2, measurement. One thing that I said earlier is that exact numbers do not contain uncertainty, but all measurements contain uncertainty. And how do we show this uncertainty? There are different ways we show it. One way we show the uncertainty is by sig figs. Sig figs gives us an indication of so if I were to eyeball, let's say, an object like this, this piece of metal, it's a metal cylinder. If I were to eyeball this, and measure its length just by estimating it, let's say, how long do you think this is? About? Yeah, over an inch, 2 inches. But you wouldn't say, that's going to be 2.138 inches. Would you do that? Or you wouldn't say that's going to be 1.78356 inches. Because, why? Why not? Because we can't measure that what would you say? We can't measure that with that level of certainty. Right? There's going to be some level of uncertainty. So how can we be so certain that it is 1.7835 inches? Does that look like 1.7835 inches to you? No, and if I'm eyeballing it, I have no confidence in that. And so in science, the way we write the numbers tells us the level of certainty or uncertainty in it. Because whenever we look at the digits, like, for example, I said this. If I measure an object that's 5 inches, it could be 1 sig fig or it could be infinite sig figs. But if this is a measurement, 5 inches measurement, then I know it's not infinite sig figs. And so I measured 5 inches. I know that's going to be how many sig figs? This is going to be 1 sig fig. 5 inches. Well, that's different than if it were 5.0 inches. A lot of people say 5 inches, 5.0 inches, the same thing. No, it's not the same thing. It's totally different. Because this is now 2 sig figs. And then some people will say, big deal, 2 sig figs, 1 sig figs, what's the difference? There's Both with 5 inches, right? And what the difference is this, the degree of uncertainty here. The degree of uncertainty here is, when we show it by sig figs, we're allowed one uncertain digit. And only one uncertain digit. All the other digits should be fairly certain. And so in this case, we have uncertainty in the 5. I don't have any other colors. And so there's only one digit here, so this must be the uncertain digit. When we go to 5.0, the uncertain digit is the 10th here. And so this is what we call a certain digit, that's an uncertain digit. And the uncertain digit is going to have a degree of uncertainty about half the unit. And so here, half the unit would be about half an inch. The units are 1 inch. 1, 2, 3, 4, 5, 6. And so it'd be plus or minus about a half inch. In other words, it'd be around 4.5 to 5.4 inches. This is what I'm eyeballing it. Whereas this, the degree of uncertainty is going to be half the unit here, which is 1/10 of an inch. It's a 0.05. And so the range here that we were talking about earlier, this would be between 4.95 and 5.04 inches. And so we call that a much higher what? Well, there's going to be a lot more certainty in this measurement than in this measurement, but what type of uncertainty or what type of certainty is that? And we had a name for that. I called it the precision or accuracy. What do I call it? Precision. And so this has a much higher precision, less uncertainty, right? Versus a measurement that's 5.00. Now for sure it's 5.0, but we don't know about the 0.01 digit, And so this is going to be the uncertain digit here. And so this is going to be much higher precision. In other words, what I'm using is a higher precision measuring tool on each of these, which is going to lower the uncertainty. This one could be a very poor measuring tool, like in our book, and I should show you the one in our book. But we have some in the lab, I think, that we can look at. So I'm going to talk more about uncertainty later, because there are some key words in uncertainty. And so one of the key words for uncertainty, these are, definitions you should know. How would you define precision? Precision is the most accurate? Sometimes the precision isn't the most accurate because, let me give you an example of something where you could have a very expensive balance. Like for example, one of the things you do when you get on the scale, a weight scale, is you have to make sure it's reading 0 with nothing on it. And in other words, if there's nobody on the scale, then it should be reading 0. But sometimes it's not. And if it's not, that's called a calibration error, and then we've got to make sure it's set to 0 with nothing on it. Normal electronic scales will do that for you. For other types of scales, you do it manually. That's called calibration. And so we could have a very expensive, a very high precision scale, but it could be inaccurate. It could be inaccurate because, it's measuring great masses, but somebody forgot to zero it at the beginning, and so it's giving you the wrong math. Now that's what we call accuracy. Accuracy is how close to the actual or true value it is. We don't know because we don't know what tool was used to measure this. Was it properly calibrated or not properly calibrated? Let's say I have a ruler, This plastic ruler is probably okay, but if it were a wood ruler, sometimes the wood shrinks due to exposure, dries out more, or maybe it expands. But if the ruler itself has shrunken over time and shriveled with age, then is it reading accurately? No, even though it could be high precision has a lot of lines. Right? And so in something like this, it depends on the tool we use. And so on this, we read between the lines. And so what we might have is something like this. We might have 0 inches and 10 inches. And the next increment would be 20 inches here. And let's say we have an object. Our object is like this. Line it up with a 0. And this is our object. And what would you say the length of this object is? Looking at this, it looks like it's about 5.03 inches. Would you agree? 5.03 inches? No. No, that's in science we'd never do that. Because we're only allowed, if I call this 5.03 inches, then I'm guessing it's 5, I'm guessing it's 0.0, and I'm guessing it's 0.03. I'm guessing 3 digits right here. I'm only allowed to guess 1 digit. If I'm only allowed to guess 1 digit, then it's got to be, well, it's between 0 and 10, I'm just going to guess it's 5 inches. And so this is a pretty poor precision ruler. This is, in other words, this is a low precision ruler because somebody else might come here and guess 4 inches or 6 inches. Who knows? It's kind of a poor precision ruler. Okay, now I could have a better precision ruler. That is, I could have a ruler that is marked at 0, marked at 1. Should I say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so I have a marking at 5 and I have a marking at 10. Now I look at the object here, and the object seems to line up right on the line here of the 5 inches. And so what should I say? Should I say that's exactly 5 inches because it lined up right on that? No, if it's exact, then it'd be an infinite number of sig figs. In this case, I'm going to guess. Because what could it be? Well, it might be 4.9, which would just be a hair below the 5 line, or it might be 5.1, which would be a hair above. And so we're going to guess that it's right on the line. It's not at 4.9, it's not at 5.1, it's at 5.0. And so that's my guess here. My guess is it's 5.0 inches. This is inches here. And this is my estimated digit because I don't see a 0.9. I'm not marked at this, so I have to read between the lines. And so when we're doing this kind of measurement, we always have to read between the lines, and we can only guess 1 digit. And that's the digit in red. This is red between the lines. So if I'm looking at 5.00 inches, that scale is going to be even higher precision. And so what does it mean to be even higher precision? It means that I might have a marking here at 4.0. And then this is going to be 4.1, 4.2, 4.3, 4.4, 4.4, 5, excuse me, 4.6, 4.7, 4.8, 4.9, 5.0. So this would be 5.0. 5.1, 5.2, 5.3, 5.4, 5.5. And so now if I look at the object here, the object is, let's say, right on the line here. If the object's right on the line, is it lined up with 4.9? No, it's not 4.9. Is it 5.1? No, it's going to be 5.0. It's right on that line to indicate it's not below, because what we're going to do is we're going to read between the lines. And so this is 4.9, but we don't have to read between the lines here. This is 5.1. What we have to do is we have to blow this up. What we're going to do is we're going to blow that up. And so we're going to have the 4.9 line here. We're going to have the 5.0 line here. And then we're going to have the 5.1 line here. And these lines are marked. And so we don't have to read or guess between the lines. Now we have our object. Our object is going to go here. And so this is what we're guessing. We're guessing it's not this. Now reading between the lines, what I normally do is I divide it in half. And so this halfway mark would be 4.95. So I do that mentally. I look, halfway between here is going to be halfway between these. Halfway between these means this, the first line is 4.90, the last line here is 5.00. And so I get 4.95, 4.96, 4.97, 4.98, 4.99, and then 5.0. And then once I do that, I read between the lines here. And so halfway between this will be 5.05 as I'm going to 5.10. And so they're going to be 10. And so this is 5.04, 5.03, 5.02, 5.01. And so what I'm doing is this. I'm guessing it's not 4.99. And I'm guessing it's not 5.01. I'm guessing it's right on 5.00. That's reading between the lines here. And so I come up with a measurement of 5.00 inches, in which the guess digit here is this one. Does that make sense? And so this is the way we read scales. And so let's get some practice reading scales here. Can you write your this is just so I can see what people are reading. Can you just write your measurement on this? I'm going to draw some on the board, and you tell me what it is. If there's some extra cards, just pass them over to this side of the room. All right, so we'll call this A. A, we're going to have something like this, where this is 0 meters, it's marked. And then this is 1 meter here, that's marked. And then the object is going to go like this. So how long is that object? All right, I just, can you compare with your neighbors and then see? Did you guys get the same? What did you guys get? 0.5 meters? So some people put 0.5 meters. You put more? What did you put? Uh-huh. We can't have a range. Okay, if you have a range between 0.5 and 0.7, we would call it 0.6 because we automatically have a range whenever we take a measurement. The range is what we write down, plus or minus, whatever, but normally we don't write it down. And so you call it 0.6. Because there's uncertainty in the 0.6, it could be plus or minus. Well, what else did people put down? 0.6? Okay, yeah, 0.5 and 0.7 would take it for sure. It's somewhere in between there, but we're only allowed to guess one digit, and then we got to put a measurement here. So 0.5, 0.6. Did anybody get anything else? Did anybody get like 0.55? What did you get? You got 0.55? Okay, 0.55 is not acceptable in science. This would not be acceptable because. Why? We're guessing two digits. We're only allowed to guess one digit. And so here you're guessing that the 0.5 first part, and you're guessing, so this is two guess digits. Even though this would be higher precision, and maybe you're very good at, maybe you're spot on, but we're just not allowed to do that. Because some people probably can estimate it to more than, some people probably can guess pretty good. They divide the space mentally. But according to the precision of the instrument, we can't do that. Okay. And so, yeah, it could be 0.55. You could be right on accurate, but we can't take it, unfortunately. And so for me, what I do here is I do this. I just go to the halfway mark. I just eyeball the halfway mark. And so the halfway mark is somewhere, here. And then if you're eyeballing that, well, then you divide the space up. And so we're guessing. And so if this is 0.5, then this would be 0.6, 0.7, 0.8, 0.9, maybe. Or let me do this. Try to get it even. 0.6. I do this in my head. 0.6, 0.7, 0.8, 0.9. I try to mentally write these, or I physically do it, to see. And then you go, is that closer to 0.5 or is that closer to 0.6, since we're only allowed one? Even though, well, it looks closer to 0.55. It looks closer to yours, but we're only allowed one, so it's either going to be a 0.5 or a 0.6. So either way, it's going to be uncertain. And so, like, if you did 0.5, then you're just saying it's closer to 0.5. If you did 0.6, you're saying it's closer to 0.6. Something like that. I might have done a 0.6 on this. It's not so easy. All right, let's do another one for B. Okay, let's say we have a line each milliliter, like this. Now, when we measure liquids are very tricky. Because do you know water molecules, do they like glass or do they hate glass? They like clean glass, they hate dirty or waxy glass. And so water's like clean glass. And so water does something weird. Water will start to climb up the sides of the glass container. And so the water molecules like glass. There's electrical attraction. And so what happens is, if I have water in here, it forms a concave surface here. Like this. I should have brought another color. And so what we do is, when we take a measurement, we have to, it's very tricky taking a measurement of water, the H2O, liquid. It's very tricky. One, we have to make sure our eyeball is correctly positioned. So for example, if our eyeball were looking up at this, then we might measure it too low. Or if we're looking down at this, we might be measuring too high of a volume. Right? We have to be perpendicular to this. If we're measuring perpendicular to this, then we're okay in our measuring cup. So not this, not this. And so if we're measuring perpendicular to this, do we go from the top? We don't go from the top, because how much the water climbs up the side is based on volume and gravity. You know, gravity is pushing it down, the electrical attractions are pulling it up. And so if we have a big container, you barely notice it, because you know the mass of water being pulled up the sides is actually quite big because of the sheer size of the container. Whereas if we have a tiny container, then the water can be pulled up much higher. And so we don't do it based on how high the water is pulled up. What we do is based on the trowel here. And so when we take a measurement, we want to measure water from the lowest point here. And so what we do is, sometimes this has a thickness to it, so we just measure from the center of that, or the base of that, either. And so we go off the center here, like this, and then we'll try to measure this line, and this would be B. I'm off a little bit. Maybe I'm looking down. Maybe I didn't draw this. Let me draw it like that. So it's more parallel. What is the volume? So when we have to write it down, go ahead and write it down and tell me what you get. Actually, just compare with the neighbor. What you're going to see is we're going to see some variation, you know, a little bit. What you get? 35 point. Okay, so we got a little bit of variation. Some people say 35.3, some people will say 35.4. And again, it's one of these things where you just, it's hard because we're eyeballing it, so we cut it in half here, mentally. And then we put in, okay, if this is 0, then this would be 1, 2, 3, 4, 5. So it looks to me like it's 35.3 rather than 35.4. But maybe I'm off. But to me this would be 35.3. The 0.3 is the guess, right? Okay. Now for metric, it's kind of nice, but what happens if we're using an English ruler? How do we do this? And so most rulers are going to be something like this. So we'll have 1 inch here, and then we'll go to 2 inches here. And then this would be 1.5 inches here. So there's a graduation here. And we could have these marked at eighths. And so it could go like this. If it's marked in eighths, there'd be 1, 2, 3, 4, 5, 6, 7, 8. That's not so great, but you get it. And so this would be 1/8. This would be 2/8. 2/8 is the same thing as 1/4. This would be 3/8. This would be 4/8. 4/8 would be the same thing as 1/2. 5/8, 6/8, 7/8, and 8/8 there, as far as the graduations go. And so 1 1/8, 1 1/4, 1 3/8, 1 1/2, etc. 6/8 is also known as 3/4. So let's have an object here. The object is going to, let's say the object continues this way. It's lined up with a 0 mark, and it goes right to here. What would the length of this object be? Does somebody have it?
I said 1 inch and 3/16.
1 inch and 3/16. You'd be okay there because it does look like, well, 3/16. Yeah, 3/16 is going to be a little short. 5/16 sounds better. But yeah, you could divide this into 16ths. You could do that, but that would mean the whole thing's uncertain. And so that 3, you're actually allowed a little bit better precision than that. This one, you know what I would say for this one? For sure it's 1 inch. There's no uncertainty there. For sure it's 1 inch. In fact, it's longer than 1 inch. And so this is 1 and, okay, now for sure it's 2/8. It's between 2/8 and 3/8. Right? But for sure it's bigger than 2/8. And so there's no uncertainty there. It's 2/8. And so where does the uncertainty come? Well, it comes in where it is between these. Where does it look like it's between? It looks like it's kind of halfway between that. And so this would be 1 and 2.58. 1 and 2.58. Now the uncertain digit is the 0.5, right? That's our guess digit. And so this is no uncertainty, no uncertainty, there's uncertainty there. And so what we do is we do this. We convert this from fraction to decimal. So can you convert this to decimal? And tell me what it comes out to. 0.3125. Now, 2.5 has how many sig figs? 8 has infinite sig figs. And so this is going to be 2 sig figs that are allowed. So 0.312, I'm going to subscript the 2. That's not allowed. And so what we have is this. For addition and subtraction, we do it based on decimal places. And so 1 is infinite sig figs, so we have an unlimited number of zeros. That's exact. You know, it's greater than exactly 1 inch. And then what we do is we add the 0.3125. Or just, I'm just going to go 0.312. And so altogether, this is going to come out to 1.312 inches. Now here we had 2 sig figs here of uncertainty, but in our answer here, we're going to have 3 sig figs. Because the rules for addition and subtraction are based on decimal places, not on sig figs. And so the uncertainty is in not the tenths, but the uncertainty is in the hundredth. And we can't have 2 guess digits, so we drop it there. And so this is going to be 1.31 inches, where the 1 is uncertain digit. Does that make sense? Now, when we have addition and subtraction, we do it based on decimal places. And so we could actually end up with more or less sig figs than in multiplication and division. All right, so I'm going to stop here with this, and we're going to talk about the lab. You know, this is